Well, it's a pleasure to welcome everybody to our first Wednesday FES speaker in series. I'm just a stand-in here for Karen, who's the regular organizer of the event. But it's a pleasure to welcome Bob Kopp here. Bob is at Rutgers University, and he is a climate scientist, geobiologist, and a climate policy scholar. He's the director of their Institute of Earth and Atmospheric Sciences and is a professor in the Earth and Planetary Science, Department of Earth and Planetary Sciences. I would say that Bob is a quite unique scholar in the sense that he is extremely interdisciplinary, and interdisciplinary in the true sense, in a way that sort of makes me, at least, quite envious, because I think that he actually is making deep contributions within multiple different disciplines, from policy and also to fundamental science. I'm most familiar with his work that he did as part of the Risky Business Project that some of you may have known of, which was the sort of Ted Steyer, Michael Bloomberg, and Hank Paulson initiative to kick off an assessment of the risks to business about climate change. From that, they had many other books, and a book that came out of that entitled The Economic Risk of Climate Change in many publications. He's also been involved in the government. He was in the U.S. Department of Energy, where he worked on the development, some of the analysis that led to our measure of the social cost of carbon. He's also a contributing author to the IPCC Fifth Assessment Report. I actually could go on and on, but it's actually Bob's talk and not mine. So today his talk is focused more in the fundamental science, where he's going to talk to us today about coasts in the time of sea level rise. So please join me in welcoming Bob for his presentation.
Great. Thank you, Matt, and thank you all for inviting me. I'm actually going to give you sort of a sampler through the perspective of sea level rise, starting with the basic science and going through some of the policy and economic implications. As Matt mentioned, I'm director of the Institute of Earth, Oceans, and Atmospheric Sciences at Rutgers. We're sort of a broad, cross-disciplinary group of people working on issues ranging from the origins of plate tectonics to climate adaptation, my interests sort of span that. But our research group, the Rutgers Earth System Science and Policy Lab, sort of has three main threads that run through it. The first thread, which is sort of my core work as a natural scientist, focuses on the reconstruction of current and past sea level change going back last century, the last few thousand years, the last couple 100,000 years, interpreting what we see in the various sorts of records we have of that, and using that information to inform projections of future changes. Another chunk of what my group does is the sort of work that Matt mentioned, much of which is happening now through a collaboration called the Climate Impact Lab, which is jointly between Rutgers, Chicago, Berkeley, and Rhodium Group, sort of focus on the integrated assessment of climate risk, sort of putting climate damages assessments on a more empirical econometric basis. And then increasingly, from working on these two end members, I've gotten involved in the area of sort of climate coastal risk assessment and resilience planning. We have, for instance, a new graduate program at Rutgers that's focused on the area of coastal climate risk and resilience, bringing together natural scientists, social scientists, engineers, and urban planners. So today, I'm going to focus on the problem of sea level rise. And I think we all have an intuitive grasp of why this is important, but one reason why this is important is sort of wrapped up in this photo you can see here of New York Harbor with the port of Newark in the foreground and New York City in the background. Right? There is a lot of capital, there are a lot of people that are exposed to changes happening along the global coastline. Currently, about 380 million people live within about 6 meters of the high tide line, areas that are potentially vulnerable to permanent flooding from sea level rise over the next couple of centuries. So we're going to look at 4 questions, and necessarily this is going to be a somewhat brief overview of these areas, but I hope we have some time for discussion at the end where we can get into more details. So those questions are, first of all, what has sea level been doing? Secondly, what might it do in the future, and what can we say about how likely different outcomes are? What would the consequences, in particular the consequences for people, be of changes in sea level? And I'll talk a little bit about what we might do about it, some of those adaptation issues. So to start with the question of what sea level has been doing. As I'm sure many of you know, most of you probably know, there are two major processes that drive global average sea level rise today. Right? As the oceans expand, as oceans warm up, they expand, and as ice on land melts and that water moves from the land to the oceans, the amount of water in the ocean increases. There's also a third, smaller contributor that has to do with the movement of liquid water from the continents to the land, mostly having to do with groundwater withdrawal. If we look over the last couple decades, roughly half of the change in global average sea level, which amounts to about 3 millimeters per year, has been due to changes in land ice, mostly due to changes in mountain glaciers, but with an increasing share coming from the polar ice sheets, particularly the Greenland ice sheet. Nearly as much has come from the uptake of heat by the ocean, and then a small fraction from these changes in water storage on land. But although ice sheets have been a small fraction of the sea level change we've observed, they're sort of what we're most concerned about, because there's a giant potential hazard locked up in the amount of ice on land. If we look at the amount of liquid water in terms of global average sea level equivalent, so how, if you were to take the water in various reservoirs on land and spread it evenly through the ocean, how much would sea level rise? What we see is that glaciers, which have dominated the land ice component, if we look at all the mountain glaciers and all the peripheral glaciers that are not part of the big continental ice sheets in the poles, we get about 70 centimeters sea level equivalent of ice, so enough water to raise global average sea level by a little over 2 feet. If you look at Greenland, if you were to melt all of Greenland, there's enough ice there to raise global average sea level by about 7 meters. And this map there on the top is a map from GRACE, a satellite that measures changes in mass at the surface of the Earth by measuring the Earth's gravitational field and the changes in the shape of it. Those red areas are areas that, based on a Princeton analysis of the GRACE data, and there are a number of groups that do this, are losing mass, and the blue areas are the areas that are gaining mass. And you see some gain because in a warmer world you have more snowfall and therefore more accumulation towards the interior of the ice sheet. So Greenland is losing mass almost all around its edges. If we look to the southern pole, the Antarctic ice sheet, we see an even larger hazard. So if we look at the West Antarctic, which we're particularly concerned about because much of that is sitting below sea level and therefore exposed to some pretty hard to understand physics related to ocean-ice interactions, there's about 5 meters of ice there. And we look at the East Antarctic ice sheet, which has been around in some form for about 30 million years, there's about 52 meters of ice there. And you can see a mixture right now of areas gaining mass and losing mass in Antarctica, but with some particular areas of concern over here in West Antarctica, especially on the Amundsen Sea embayment. So that's sort of the global average picture. But if we try to interpret what's happened in the past, or we try to project what's happened in the future, we have to deal with the fact that people don't live on the global average. Right? It's nice to know that global average temperature today is 1 degree warmer than it was 150 years ago. But what does that actually mean for an individual, for a city, et cetera? It's nice to know that global average sea level rose by about 6 inches over the course of the 20th century. But what does that mean for a particular place? And when you start doing that, the physics become much more complex. Not only do we have to worry about the changes in the amount of heat stored in the ocean, but we also have to worry about changes in ocean circulation and atmospheric circulation that move water around. Not only do we have to worry about the amount of ice melting on land, but we also have to worry about the way those changes in the amount of where mass is on the planet affects the planet's gravitational field, its rotation, and causes the crust to deform. If you melt an ice sheet, because you're taking a big concentrated mass of ice and distributing that mass through the ocean, you actually get a sea level fall within a couple thousand kilometers of the ice sheet. So if you melt ice on Greenland, sea level falls in Scotland, even though global average sea level goes up. And then on top of that, The land, which is the base from which we measure sea level using tide gauges and reconstruct sea level using geological records, has a variety of processes that affect it, from the long-term response to past changes of mass distribution, to movements by tectonics, to compaction of sediments. So all of these processes, have to be taken into account when we think about either interpreting the past or looking forward. So let's talk for a little bit about interpreting the past. One source of information we have about past changes for the last 20-some years, we have satellite observations of the height of the sea surface, which is quite useful. It's not exactly the same as sea level, which is measured with respect to changes in the land as well as the height of the sea. But that only gives us a 20 or so year record. So to go back further, we have to look at tide gauges, which in their simplest form are basically a stick stuck in the ground and a floating bit that measures how high the water surface is relative to the thing that's stuck in the ground. This photo here is a photo of the Battery tide gauge at the southern tip of Manhattan. It's been decked out with some solar panels and some other things, but fundamentally it's a stick stuck in the ground. This is a measurement of annual average sea level from the New York City tide gauge, which was started in the 1850s, underwent a period without data for a couple decades later in the 19th century. And you can see this gradual upward trend, some of which is due to geological processes. The land is subsiding as a result of the changes associated with the fact that Manhattan used to be under a giant ice sheet, and some in the 20th century due to global scale changes. So we would like to know what those global scale changes are. So to do that, we build a statistical model has the data set, the variety of data we can get in the global tide gauge database. And this map here shows you where those data are, and the color is representing the time periods for which the data are covered. So you can see some challenges already with the tide gauge data set. In Europe and parts of North America, they go back to the middle or early 19th century, but in much of the world, tide gauge data only became available after World War II. So the basic model, and this is something I'm going to gloss over, but I'm happy to discuss more, is a Bayesian model that's non-parametric. It's based on the idea that there are different processes that have different spatial scales on which they relate to one another and different temporal scales of variability. And so from the spatial patterns and temporal patterns that we can observe, we estimate what the overall field is. So the basic idea in this model is that there is some globally uniform term, which is associated with things like the average uptake of heat by the ocean, a term that's associated with the different sources of ice on land and the different spatial patterns that are associated with them. Again, as I mentioned, like near a melting ice source, you actually get to sea level fall because of things like the changes in the gravitational field. There's a component that has to do with changes in ocean circulation and changes in where heat is distributed in the ocean, from which we know something from ocean models that we can use to interact with the data. There's a component that has to do with the ongoing response to the end of the last ice age, and then there's other things that we treat as noise. So that's the general model. At the bottom of this figure here, I'm showing you results from 5 tide gauges. So the red are the annual observations, and the gray is the model fit. As you can see, the model explains the data reasonably well. So from this model, we can do things like reconstruct the overall field of sea level change. So this is a reconstruction of the average rate of sea level rise from 1901 to 1990. And you can see some of the variability in here. This area of deep red, for instance, is on, and this blue here is associated with the response to the end of the last ice age, as well as some changes in ocean circulation. You can see here these areas of deep blue, again, some associated with the response to the end of the last ice age, some associated with ongoing melt. And perhaps more interesting than looking at the global, at the global map of local changes is the common global signal, the thing that relates to those changes in land ice and ocean heat uptake. This is our curve. There are other people who use different statistical approaches. I prefer ours, but this is our reconstruction. They all come to relatively similar pictures. This is a global average sea level rise from 1880 to 2010. And what we find is that from 1901 to 1990, global average sea level rise was about 1.2 millimeters per year, about half an inch per decade. And starting in the early 1990s, it rose about 2.5 times faster, so now rising about 3 millimeters per year. And I should mention this work was done in collaboration with the colleagues pictured here, Jerry Mitrovica, who's on the faculty at Harvard, Carling Hay, former postdoc who just started at Boston College, and Eric Morrow, another former postdoc. But one obvious question is, how unusual is this? Maybe sea level does this in support of internal variability. You know, if you were to go back to any random century, maybe you would see variations like that. To get a sense of how unusual it is, you have to go before the tide gauge record. So we have to turn to geology. So there's a variety of different ways geologists have for reconstructing past local sea level changes. One of the highest resolutions come from salt marsh records. This is a photo taken by my colleague Ben Horton of his team in the field in Newfoundland a couple of years ago. So this is a salt marsh. And the basic idea here is they take a core of sediments from the salt marsh and then look at the layers of sediments in the core, look at the microfossils in the core, which are tied to different places in the tidal zone. So it can tell you, you're near mean tide level or near the high tide line. And from that reconstruction and some age model, which can come from sources like carbon-14 or various pollution horizons, you reconstruct a local record of sea level change. This is a map of the different sites and different types of data that go into our reconstruction for the last 3,000 years. So these green dots are salt marsh or mangrove records. The ones in the Mediterranean include things like Roman fish tanks, which had to be built in the intertidal zone, and so give you some indicators for a very particular point in time. And there are other records like coral microatolls from the South Pacific. And this database was compiled by my colleagues Ben Horton, Andy Kemp, who is at Tufts, and Roland Garrels at York. So the model here is simpler because there's less data, and therefore you can get less process specificity. So the idea here is there's some common global signal that we see in all the records, plus a local linear signal that picks up things like slow processes like the ongoing response to the end of the last ice age, glacial isostatic adjustment, plus a regional nonlinear term that may include things like spatial patterns associated with ice sheet melt or changes in atmosphere-ocean circulation and noise. And here are some examples of the data. So the data are in red, so the boxes representing both uncertainty and age, which you have to deal with when you're talking about geology, and uncertainty and height that have to do with how you interpret things like those microfossils. And then the gray and the black are the model fit to the data. So again, the point here, the model fits the data. And it can reconstruct with less specificity once you get away from the points where you actually have data, the sea level field. So you can see some interesting variability, for instance, in this slice, which is from 700 to 14 CE, along the coast of the United States, where we do actually have quite a bit of data. And notice all of the numbers here are relatively small. You're talking about a couple tenths of millimeters per year. Global average signal of about a decline of about 0.1 millimeters per year. And again, this may be the more interesting curve here. This is that common global signal. And you can see some of the high frequency ups and downs, where high frequency means sort of century scale, are probably just model artifacts. They're all well within noise and have to do with the model going up and down and trying to hit data. But there are some features that are pretty robust to various cross-validation approaches. For instance, this decline from 1,000 to 1,400 CE associated with a period we might call the Little Ice Age, a period when there's about a 0.2 degrees Celsius fall in global average temperature, is robust. This one is controlled by a small amount of data, and so we're still not sure about this. And then obviously you have this signal at the end that's quite precise once you have tide gauges as well as geological data. The average over the 20th century, from 1901 to 2000, global average sea level rise was about 1.4 millimeters per year. And we can say, based on this analysis with 95% probability, that it was faster than any century since at least 800 BCE, when the quality of the record declines. Or, as our previous president said, we're seeing the fastest rise in sea levels in nearly 3,000 years. So that's the last few thousand years. And I don't have time to talk about longer periods except to raise a flag that earlier periods tell us. So these are coral reefs. They're about 125,000 years ago. And if you know anything about corals, you know they grow below sea level. So the fact that they're over here about 2 meters above sea level indicates that at the time these reefs formed 125,000 years ago, sea level, at least locally here in the Bahamas, was higher than it is today. And we have some ongoing work with my postdoc, Erica Ash, and my colleague, Andrea Dutton, sort of looking at some of these time periods more. But sort of based on the overall literature, we can say some things about past sea level. So this is a figure from the U.S. government's Climate Science Special Report, which came out earlier this year. There's a lot in here, but the key thing I want to draw your attention to is that 125,000 years ago, global average temperature was somewhere between about 0.8 and 2 degrees Celsius above pre-industrial. So it could have been around what it is today. It could have been a little warmer. And global average sea level, based on our work and Andrea's work, was probably around 6 to 9 meters higher than today. So there's difficulties because things like changes in Earth's orbit were different in interpreting that directly. But this may be a hint of what sort of the long-term response to 1 to 2 degrees of global average warming would be. But let's get more specific on the question of what might sea level do in the future and how likely different outcomes are. So many of you, I hope, are familiar with the different scenarios that are sort of used in the climate modeling community, but for those of you who are not, one uncertainty I'm not going to try to address in this talk is the uncertainty in what humans are going to do in terms of their emissions over the next 80 years. And in the climate science community in general, we sort of remove that uncertainty by looking at different scenarios. The scenarios here are called representative concentration pathways, and we're going to focus on 3 of them. And these have been developed over the last decade by the climate modeling and integrated assessment communities. So this red curve here, that's a pathway known as RCP 8.5. And I would call that just a fossil fuel intensive growth trajectory. I don't think we're actually all the way up there, but if you were to extrapolate some of the rapid growth you saw in the last decade forward in emissions, we could be on it. So this trajectory goes from around 40 billion tons of CO2 per year today to nearly twice that in 2050 and continued growth thereafter. This middle trajectory, RCP 4.5, is probably a little bit more optimistic than where current policy would take us, but it sort of plateaus emissions at their current level and then brings them down in the second half of the century. And this lowest scenario, RCP 2.6, is the only one of these 3 that's consistent with the aspirational goals set out in the Paris Agreement of limiting warming to 2 degrees C and bringing net emissions to 0 in the second half of the century. This one basically starts decline now, cuts emissions by about 70% globally by the middle of the century and brings them to negative values in the last 2 decades of the century. So these are the 3 scenarios I'll refer back to a few times. So there are a couple of approaches we can think about when projecting forward. If you're economists, you might think about these as sort of reduced form versus structural models. I would call it a statistical versus a process model. And so one approach, also known in the literature as a semi-empirical model, is to consider the past relationship between temperature and sea level. And this is part of our Common Era paper that Klaus Bitterman, currently a postdoc at Tufts, worked on. And it's a pretty simple model. The basic idea is that the rate that for a given level of temperature, there is some equilibrium sea level response, and there is some rate of change approaching that response that has to do with the degree to which you're out of equilibrium. So this analysis is basically based on comparing the global sea level curve to two different global temperature reconstructions from other geological proxies and then projecting forward. And that's what's shown here. So the different lines are median projections for the three different scenarios, and this is the 5th to 95th percentile on the right in 2100 for the three different scenarios. So based on these sort of statistical relationship, we get between about 50 and 130 centimeters of global average sea level rise under a high emission scenario over the course of this century, about 20 to 60 under a low emissions scenario. But this sort of statistical approach projects global changes, and I spent a fair bit of time telling you why you have to think about local changes, and is calibrated from a time period where the dominant processes were different. Thermal expansion and mountain glaciers, perhaps some regional ocean dynamics, dominated sea level change over the last 2,000 years. And using this approach sort of assumes that those sorts of processes probably will continue to dominate into the future. We're not sure that there are, as we talked about the growing role of the polar ice sheets. So another approach is to look at the individual contributors and draw upon different sources of information to try to estimate the future changes in these. And so this is some work we've done in a different paper. We're taking a sort of probabilistic approach here where we try to estimate for each of these dominant contributions sort of a probability distribution. It's a little different than what the Intergovernmental Panel on Climate Change did, but not especially different. Other than that, we're trying to look both at the tail risk as well as the sort of central range. So, we have changes in land water storage, ice sheets, glaciers, thermal expansion and ocean dynamics, and other non-climatic processes. And for sake of time, I'm not going to get into a great deal of detail in what we do with each of these. One thing I will say is that for the ice sheets, which are the hardest thing to build a physical model of, we rely in this assessment on the assessment of the Intergovernmental Panel on Climate Change's 5th assessment report from 2013 to calibrate the central range of ice sheet projections. And then we use information from a structured expert elicitation to try to understand how that central range relates to sort of the tails of the distribution. For other components, we draw upon information from climate models and from glacier mass balance models forced by climate models. And then we take into account the local effects that cause the sea level change associated with ice sheets to differ from the global average. And I should mention that this approach has gotten a fair bit of uptake in sort of policy circles in the United States. It's been used by a broad range of stakeholders from the Congressional Budget Office to a report we did for New Jersey. It played an important role in the sea level projections developed for the current national climate assessment, work in California, Oregon, and a couple others. So if we look at this approach, and what I'm going to call bottom-up accounting, so here we're looking from 2000 to 2100, our three different scenarios, the median projections in these curves, the 5th to 95th percentile at the right side, and this is a global median projection for the high emission scenario, just to give you a flavor of some of the geographic variability. What we find is for sort of a central projections, there's not much difference between a high and low emission scenarios in the first half of the century. So in 2030, we're looking at about 10 to 20 centimeters of global average sea level rise, regardless of emissions. By 2050, basically 20 to 40 centimeters, regardless of emissions. But by 2100, there starts to be some difference. 30 to 80 centimeters under the lowest scenario, 50 to 120 centimeters under the highest scenario. And we can compare this structural model to the reduced form model I showed earlier. So just as a reminder, those are the values we just talked about. If we looked at the statistical projections, they line up remarkably well. Almost identical for the high emission scenario, a little bit fatter tail on the bottom-up projections for the low emission scenario, but pretty good agreement. But I think this raises a question. Is this good? Should we expect the historical relationships of the last 2 millennia to be a good predictor of 21st century sea level change? And I would say perhaps not. Right? As we said, ice sheets are playing a growing role, And there's some pretty remarkable physics that happens where you have an ice sheet that interact with the oceans. Some of you have probably seen the series of images I'm going to show you here before, but just for orientation, so this, where you can see the mountains, this is ice sheet, it's ice on land. Here, this is an ice shelf, so it's floating ice. If floating ice melts, it doesn't have a direct effect on sea level, but the ice on shelf plays an important role in buttressing the ice sheet, so sort of slowing its flow from the continent to the ocean, and also preventing the formation of sort of unshielded ice cliffs, which can become structurally unstable. So this is a 40-kilometer scale bar, about 24 miles. I'm going to show you images from a month in 2002. So mid-February, third week of February, early March. Like this ice shelf sort of basically disintegrated in the course of a month, removing its buttressing effect, allowing the formation of ice cliffs at the edge of the ice sheet that can become unstable. So we're particularly concerned about two forms of instability associated with the interactions between the oceans and the ice sheet. So one is called marine ice sheet instability, and this is a figure from a paper by my collaborators, Rob DeCanto and David Pollard. And the basic idea with marine ice sheet instability is that you can have warm ocean waters penetrating underneath an ice shelf to get at the ice sheet, eating away at the ice sheet, exposing a larger cross-sectional area of the ice sheet to warm ocean waters, and thus creating a self-reinforcing cycle that only ends when you get a change in the slope of the basin holding the ice sheet. Another form of instability, and so the marine ice sheet instability, people have been looking at it for a few decades. The marine ice cliff instability really has only been considered a major potential contributor to sea level change recently. But the idea here is if you lose your ice shelf, which can happen, as we just saw, more rapidly than one might have thought because of things like a hydrofracturing caused by the pooling of meltwater at the surface of the ice shelf and the burrowing of that meltwater into the ice shelf. You get ice cliffs, which can only grow so high before they become structurally unstable, as you can see here in this photo from Helheim Glacier in Greenland, and then collapse, roll back, creating another ice cliff, and again get into this sort of positive feedback loop. So this is really cutting-edge science, and still pretty controversial how large a role it can play, whether there are other feedbacks that might operate in a different direction. But to get a sense of what it implies for global and local sea level changes, we worked with Rob and Dave and basically substituted their model into our overall framework to look at the implications for sea level changes. So this is in a paper that was published last month in Earth's Future. Down here, we're looking at the projections I showed you earlier. I'm going to show you now the projections when we do that substitution here on the same axes. So two conclusions. One is that it doesn't matter much through 2050, regardless of how you treat the ice sheets. The relevant physics underlying those sorts of marine ice cliff and marine ice shelf instability don't really kick in the first half of the century. And there is very likely to be between about 1/2 foot and 1.5 feet of global average sea level rise in the first 5 decades of the century. And it's virtually certain to be less than 2 feet of sea level rise. But for 2100, there was a very large effect, especially under a high emission scenario, where instead of 50 to 120 centimeters, we get 90 to 240 centimeters. Very much less change if we look at a low emission scenario. So this suggests increasing evidence that there's a big sea level difference between a Paris Agreement consistent world, reflected by that low emission scenario, and more modest emissions reductions. And you can also see that if you look at the middle scenario, the one perhaps closest to the trajectory we're on, if a little bit more optimistic, if you look back at how that changes. Another sort of more subtle outcome is that because the physics that give rise to high-end sea level outcomes don't play a major role right now, large-scale observations of global average sea level or of continent-wide changes in the ice sheet, won't be able to distinguish between a high-end outcome which is represented here by one leading to 2 meters of global sea level change, and a low-end outcome, one represented here leading to 50 centimeters of global sea level change. So next figure, I'm going to sort of invert the figure here at the bottom and ask, okay, if you only had this global average sea level curve and you had to project, say, here in 2018, what sea level rise at the end of the century would be, what would you estimate? So you're going to see sort of projections like start out broad early in the century and narrow as you move along. So this red curve, that's what you would project based on observations in a world that is headed towards 200 centimeters and what you would project in a world that's headed towards 50 centimeters. And you can see that these pathways don't really diverge until after 2050. So if we want to distinguish sooner, we're going to need advances in our understanding of the small-scale physics of ice sheets. Global and continental scale observations won't do it. Better understanding of how ice sheets behave during past warm periods would also help by providing a check on our models of small-scale physics. And we greatly reduce the odds of a high-end outcome by reducing emissions, right? You can't get on that 2-meter trajectory based on our analysis if you're on a low-emission scenario. And it's pretty hard even if you're on a moderate emission scenario. But in the meantime, we will have to make decisions cognizant that it may take decades to resolve this sort of deep uncertainty in ice sheet behavior. And now let's talk a little bit about the consequences. So the most obvious consequence of sea level rise is permanent flooding of land because as it is submerged beneath the waves. This is Lee Fort Cemetery in Leeville, Louisiana, which is one of the areas in the world that have experienced, due primarily to local processes, with fast sea level rise over the course of the last century. Sea level in Grand Isle, Louisiana, nearby, rose by about 2 feet from 1947 to 2015. Right, really rapid. And as a consequence, things like this cemetery are no longer above water. Based on work we've done that Matt mentioned in my introduction in the Risky Business, for the Risky Business Project, which was published in this book from Columbia Press, there is about $230 to $460 billion of current U.S. property that's threatened by the sea level rise projected for the next 3 decades. But before we get to permanent inundation in most regions, we will deal with more frequent flooding, more frequent tidal flooding, more frequent storm flooding. And many areas already have to deal with this. This photo, which looks a little better in my screen than it does on yours, is a photo taken by my former student Maya Buchanan in Broad Channel in Jamaica Bay area of Queens, near JFK Airport. This is not a sunny day, but it is a day without storms, and you have inundation of the roads. This is what's called nuisance flooding by the National Weather Service. And although it's a nuisance, it also causes some economic damage and may be, in fact, the most important in changing behavior. If you're getting flooded 20 times a year at this level, that may be more likely to change your behavior than one really bad storm. And sea level rise is already greatly increasing nuisance flooding. This bar chart from my colleagues down the road in Princeton at Climate Central is showing you the number of nuisance flooding days per year at Atlantic City. And so, this is not per year, this is per decade, so divide by 10. And you can see it's gone up by about a factor of 10 from the 1950s to today. Also on this is a distinction between that amount of sea level rise we can attribute to the warming that we've experienced since 1900, shown in orange, and that which would have happened anyway. And so you can see at this point, anthropogenic processes, global anthropogenic processes, are the dominant driver of nuisance flooding in Atlantic City. Sea level rise also makes storm flooding more severe because if you have a higher sea level base, you get more damage from the same amount of storm surge. And we've previously estimated that global sea level rise from 1880 to 2012 exposed about 80,000 additional people in New York City and New Jersey to flooding during Superstorm Sandy. Here's a picture of Ship Bottom, New Jersey, immediately after Sandy and when it was not flooded by a storm. And the expected number of flood events can change extremely significantly with sea level rise. This is for a moderate emission scenario based out of the, moderate central projection for a high emission scenario based on the analysis we did for New Jersey. So this is looking at the expected number of storms that exceeding 6 feet of flooding at Atlantic City, which in 2012 would have been called a 1 in 10 year flood, so a 10% chance in any given year. With projected sea level rise through 2045, this becomes about a 1 in 2 year storm, a 50% chance. By 2062, basically the average annual storm, or not the average annual maximum storm. And by 2100, this is daily flooding at high tide. Right, so that's a pretty significant change. Based on work we did in collaboration with RMS, a consultancy that sort of works with insurance companies to look at their exposure, this is the change in coastal storm damage we would get in the United States. So here, RMS took a variety of different sea level rise projections from our Monte Carlo samples, ran them through their model, and then, so basically had simulated storms on top of different sea levels. And then we pulled out, for different scenarios, what the change in storm damages as a percent of GDP would be for different global average sea level rise. And that's just showing you the distribution of those damages for a late century, middle of the road RCP 8.5 suggestion. In the current economy, so assuming no changes in where people or capital are, no changes in prices, each inch of global mean sea level rise would increase U.S. average annual storm damages by about each centimeter, by about $200 million. And it's quadratic in roughly, as you can see in this plot, so that would be increasing to about $500 million per centimeter with 1 meter of rise. So if we take those estimates and apply them to our different sea level rise projections, we get under our projections without the ice cliff and ice shelf instabilities, about $20 to $50 billion a year of storm damages under a high emission scenario, under about $10 to $30 billion under a low emissions scenario, with that higher number increasing to about $30 to $130 billion a year when you factor in the potential effects of those stabilities. Sandy was about a $70 billion storm. This year, the three large hurricanes we experienced, the current estimates are, I believe that's around $200 billion of damage. I'm not sure whether that factors in all the damages that have yet to be repaired in Puerto Rico, or the loss of life there. But this is sort of gives you a sense of what's at risk here. So very briefly, what might we do about it? So one thing that should be clear is that our mitigation policy choices will affect the sea level to which we have to adapt. But we will have to adapt to some sea level rise even under the strongest mitigation scenario. Even under RCP 2.6, we're still looking about 1 to 3 feet of global average sea level rise we'll have to do something with. So what do we do? Do you rebuild essentially unchanged? Maybe even continue to gentrify the coast, put a little more capital there, and assume that the current system of subsidies will support that. This is a photo from Oakwood Beach, New Jersey, which was significantly damaged during Sandy. And you can see some very fancy new houses with their doors, very inviting for the ocean to come right in. Or do we raise our houses and otherwise modify our communities to accommodate occasional flooding? This is a photo from Manasquan, New Jersey, where the gentleman here has lifted his house, I guess probably about 10 feet, and created himself a nice parking spot and a nice view of the ocean. But one thing we have to remember is that this is not really an individual decision. Individuals can do things like this, but if you elevate homes and don't elevate infrastructure, you can be in this nice home, not flooded, but cut off without, without sewage or electricity. Not really sustainable necessarily unless you make those collective decisions and think about collective risk reduction. Or do we build hard infrastructure to project? This is a visualization of the proposed East Side Coastal Resiliency Project, which is a mixture of seawalls and removable floodgates built over with some parkland there. But if we take this approach, as we saw with Hurricane Katrina, you also have to think about what your contingency plans are when this hard structure fails. And you also have to deal with the fact that there is this deep uncertainty in sea level rise, and therefore you'll need to be able to deal with what happens if sea level rise ends up being on a higher trajectory than you've planned for. Do we expand protective natural infrastructure, like these new oyster beds that have been put in place in Jamaica Bay, and can dampen the wave energy that can cause some of the damages associated with the storm? Or do we relocate to higher ground? This is a photo from Oakwood Beach on Staten Island, which is one of the few areas after Sandy that collectively took a buyout plan. I believe around 200 people got bowed out there, and they're slowly giving over the neighborhood to wildlife. So where possible, one of the key tools may be flexible adaptation pathways, right? We don't know whether we're on that 2-foot trajectory or the 7-foot trajectory, and we may not know for several decades. So when you're building an infrastructure project or you're making a zoning decision that has an 80-year time horizon, it's probably a good idea to think about those contingencies now. This is an example from the Thames 2100 project in the UK. And this very complicated figure is basically mapping out different levels of water rise, different actions that would be workable under those different levels, and then showing you an illustrative pathway one might take through these different actions based on new information coming in. Another question to ask is, how much does this cost, and how do people actually make decisions about this? This is an area that really needs a lot of work, in my opinion. There are some simple sort of global scale benefit cost analyses that basically rely upon heuristics and broad generalizations. This is a nice study done by Delavane Diaz a couple of years ago, where basically she took all the coastal segments in the world and gave them an option of no adaptation, retreat, or protect to various levels, and then did a benefit cost optimization. And then she found that heuristically, least cost in the United States, least cost protection expenditures would be about 3 to 5% of unprotected flood damages and avoid about 80 to 90% of total costs. If you take her model at face value, and there's a lot of detailed work that needs to go into understanding these questions, her least cost protections expenditures would amount to about $4 billion annually by 2050. And that's not NPV, apologies for that. That's 2050 values. But what all of these sorts of heuristic studies also indicate for the US is that we could avoid about 80 to 90% of flood damages today through least cost protection expenditures. So at the moment, that least cost optimization does not at all describe the relevant behaviors, and this is another important area for research. One thing we're trying to do at Rutgers, and then I'll close, is trying to build these sort of interdisciplinary scientists who can think about these questions. So we have our Coastal Climate Risk and Resilience Initiative, and if you have undergrads or you have a master's student who might be thinking about a PhD, I'd encourage you, if this is an interest, to point them in this direction. So we're taking natural scientists, social scientists, engineers, urban planners together, getting them to learn how to talk to one another, how to work with stakeholders. We just had a project completed with the town of Union Beach, looking at resilience strategies there. And we're very excited about this moving forward. I think we really need people working across these boundaries in order to be able to deal with some of these deeply uncertain and challenging questions. So thank you.
Hi, my name is David McCarty. I'm a second year MEM here. And I just want to say thank you. And my question is sea level rise, or is sea level actually level polar, across the poles, or is there a centrifugal force effect of the Earth's rotation that would say if we met the averages, it will rise more around the equator than it would in northern or southern regions?
So a couple of questions. So it's not actually that. So there's a surface called a geoid, which is basically a solution to that equilibrium question. And there is a difference between the poles and the equators. It doesn't really affect any of these decisions of this analysis because everything we're looking at are changes relative to the geoid. But it is exactly those changes, those factors that, well, for instance, if you look here, these are the fingerprints of relative sea level change that I've sort of hinted at earlier, associated with melting in Greenland or melting in West Antarctica. And you can see right near a sea level, near a melting ice sheet, you get a sea level fall. That's because of that gravitational change. Here in West Antarctica, you can also see clearly this sort of quadrupole pattern. That's because of the way the Earth's rotation changes in response, and exactly that sort of phenomena you were talking about. The other thing is more generally, rotation, of course, affects all of the circulation on the planet, so including things like the Gulf Stream, which you can see here, which sets up an important regional difference in sea level between the southeastern U.S. and the northeastern U.S., and potential changes in the Gulf Stream, which can be driven by changes in the pole to equator temperature gradient or by changes in freshwater input, also have a potentially important sea level effect.
Thank you. My question is related to the effects, relative contribution to sea level rise between uncertainty in ice sheets and different scenarios of emissions. So your talk said that the variability caused by uncertainties of behavior of Antarctic ice sheet could be anywhere between 0.5 meter to 2 meters versus different emission scenarios from RCP 2.6, somewhere about a foot, to RCP 8.5 over a meter. It seemed to me that the uncertainty in ice sheet behavior would cause twice as much as sea level rise variability uncertainty than human behavior. Would you?
So, all right. So let's focus on the second plot because these are a little complicated. So this is the fraction of overall variance in the uncertainty that in global mean sea level attributable to different causes. So this is, well, actually we can look at both of them. They're not that hard to look at 2 versus 1. So these are our projections, and from our 2014 paper, these are the ones where we've substituted in the alternative treatment of the Antarctic ice sheet. And so what you can read here is, like, for instance, in this version, uncertainty in TE, thermal expansion, accounts for about 70% of the overall uncertainty, physical uncertainty. This yellow wedge is a wedge associated with scenario uncertainty, assuming that your base scenario is this middle emission scenario, RCP 4.5, and that the high emissions and low emission scenarios are equally likely, as well as the middle emission scenario. This red, when you factor in the uncertainty in the ice sheet physics in Antarctica, that dominates sea level uncertainty through much of the century. But you see this growing share that's attributable to the spread among those scenarios. And so, by the time you get to the end of the century, the large, or at least the majority of all the spread in the sea level scenarios is attributable to the question of which scenario you're on, as opposed to the uncertainty in the physical response to a given scenario. You can also see that in a little bit simpler form, if I can find my mouse. Let's see, there we go. If you look just at those curves we were looking at earlier, and I still don't see my mouse, so sorry, apologies. There we go. So if you look, this is the 5th to 95th percentile range of uncertainty and how the climate system and the sea level respond to a particular scenario. And these are the different scenarios. And you can simply see that there's essentially no overlap between a low emission scenario when you do this treatment of Antarctica and a high emission scenario. So that tells you there's a large amount of the uncertainty that's attributable to the differences between those scenarios. Okay.